Hi everyone, it's Mike from Morton Lights here. Today I want to discuss my passive PoE solution that I use for my controllers, take you through it all and whatever. There's been a few questions on Facebook about how it's been done, and I planned to record this anyway, so I thought, hey, why not do it now? So for a bit of history, obviously, majority of people place their power supplies within their control boxes, right, which powers both the controller and the pixels. A Falcon V4, for example, will have its power switch set to take power from the V2 input, being the pixels 9 through to 16, and then the voltage switch will be set up to match the pixel voltage, whether that be 12 or 5 volts, so the controller gets the correct power. Now, if you're one to power your showdown outside of hours, it means that the controller becomes inaccessible when the power goes out. It's no longer switched on, it's not visible on the network, you can't get to the management interface, you can't do anything with it from X lights or make any things. So therefore, if you want to make any adjustments, you've got to power your whole show on, which is can be quite a pain. Personally, I make quite a few tweaks and changes throughout the season. For example, moving props around when they blow about the yard, or adding new props in, or what have you. So I like to have the entire show accessible to push the configs, to run any new sequences, like upload them and whatever as required. And to go through and power up everything, wait for the controllers to boot, etc., would just be a pain in the butt. So to get around having to power the whole show on, I have my controllers powered from a different power source to the pixels. There's a couple of ways to achieve it. And you could have a separate small power supply within the enclosure, which doesn't get powered down, which would power just the controller logic. But that then requires you to have two AC cords into the enclosure, one which is switched on and off, and one which is powered all the time. Or you'd need a smart switch within the enclosure controlling this pixel power. Alternatively, the pixels could be supplied externally by using power injection, not use anything through the controller's capabilities, and just the small power supply within controller enclosure, but then that has its own complexities, and using the existing fusing and power delivery within controllers is actually very convenient. So the third way is to power the controller from a central location using power over the Ethernet. We know the Ethernet cable's always there, so hey, why not use it? Now, there's a couple of different ways of doing this. One is using PoE adapters. You can get special ones which will take your normal PoE, break it back out. I use one of those on a Raspberry Pi, which powers my GPS and plane tracking Raspberry Pi, but I opted not to do that in this particular case. Controllers which are currently on the market are shipped with only 100 meg Ethernet interfaces. Falcons, the Beaglebones and whatever, Raspberry Pi 3B Plus and later have gig. They'll drop back to 100 meg using what I'm about to explain. And the reason why the 100 meg is really, really cool and convenient is it actually only uses 2 of the 4 pairs within the Ethernet cable for the network connectivity, being pairs 2 and 3, which is the orange and green pairs. The 2 remaining pairs, blue and brown, are spare. That's historical. The blue pair 1, was typically used for a telephone line. So then Ethernet, when it started to become popular, used to sit on pairs 2 and 3, which wouldn't be used by that telephone line, and you could use the same cable. So my solution is then using the 2 spares, the blue and brown pair, to deliver power to the controller. It's very important, though, to remember that this is not a standards-based PoE. For example, 802.3 AF or AT. You just can't connect any old PoE switch into the controller and expect it to work. You will damage things. And I'll get into the technical reasons for that why. Ubiquiti do something very similar on their older carrier grade gear with the 24-volt passive PoE. And in fact, you could use something like a Ubiquiti Edge switch, which supports this passive PoE, to power the controllers. However, I have specifically used 12 volts, not 24 volts, due to some other limitations and some convenience, which I'll get into as well. It just makes life a little bit easier using the 12 volts. So how does it all work? Have a look at this diagram, which kind of shows it all, how it all pieces together. On the left of the diagram is essentially what's in my main control box. That houses the network switch, it's got a power supply. On the right-hand side of the diagram, we've got the controllers. And in the middle, those blue tubes are essentially the Ethernet cables. Each Ethernet cable, as I mentioned, has got 4 pairs, the blue, orange, green, and brown pair. And just the green and orange are used for the Ethernet signal, and blue and brown we use for PoE. At the main control box end, which is the supply end, I split out the blue and brown pair independent of the green and orange. An 8P8C connector, or incorrectly known as an RJ45 connector, is crimped onto the green and orange pairs only, which then plugs into the network switch. The blue and brown pairs are connected to the 12-volt and ground lines, respectively, of a small computer power supply. Now, I've picked that blue and brown being positive and negative on purpose. In my own mind, it made sense that the ground is brown, therefore Earth is brown, and negative is brown, therefore, and the sky, which is up high, like the voltage up high, is blue. That was my reasoning behind it, and it actually coincides with something later, which I'll talk about. The power supply that's in that side of the enclosure operates 24/7 with a control box. Now, each pair is a pair, 2 wires. I use both the color and the white pair in parallel for a particular line. So the blue and blue-white are the positive, and the brown-white wire are the negative or ground connection. On the right-hand side at the far end at the controllers, we've got a similar approach to extract the power. The green and the orange pairs go out to an 8P8C crimped connector, which then plugs into the network jack on the controller. The 2 other cables from the blue and brown pairs get a ferrule on each of the pairs, twisted together, and then a ferrule, generally red and black, sometimes red and blue, which are then connected to the controller power input. So on an F16V4, this goes into the VX connector. The input switch would be then set to external, and the voltage switch to the 7 to 13 volts because we're using a 12-volt input. And on the Hanson boards, they have a separate controller power header to the pixel power header, so it connects straight to the 24-volt portion of that power header. And that's it. The Ethernet flows through the green-orange, the power flows through the blue-brown, and the controllers are powered up all the time from the central control box. So let's have a look at some pictures depicting the actual installation that I have rather than just a diagram. So this first picture here shows how the Ethernet cables are split. They're coming into the control box on the left-hand side there through a 4-way solar grommet. 4 leads, you can see there's a bit of heat shrink there. The black heat shrink going down has got the blue and the brown pairs in it, and then I've reused the stripped blue jacket from the Cat5 cable for the Ethernet stuff going to the switch, and the second picture here just gives a bit more of an in-focus shot of the switch of the same connections. This next picture shows that big bundle of cables in the middle, the black bundle. You can see the split pairs coming from the top through the heat shrink, goes into another lot of heat shrink into that black and white cable at the bottom. That then connects onto the yellow and black, being the 12-volt and ground out of the computer power supply. That 12-volt is also powering a few other things as well. So there's cables going elsewhere, and the 5-volt from the computer power supply is also powering a few other things in that box. And finally, this last picture of the main control box shows how the pairs are crimped within the 8P8C connector. So the orange pair is going to pins 1 and 2. The green pair is going to pins 3 and 6, which is standard 568B wiring. If you're a 568A person, the green and the orange would be swapped, but obviously make sure that that's different at the far end. It's a little bit fiddly getting especially the 3-6 pair split and into the right holes without having all 8 wires there, but because I've crimped, I don't know, thousands of these plugs throughout my lifetime, it doesn't take too long and too much practice to get in there. So that's basically how it all works, and they plug into the switch. At the controller end, here's a picture of my HE123 differential controller. So the 12 blue leads coming out the top, they're the differential lines. In the bottom right-hand corner there, you can see there's a single grommet. That grommet or gland has got the Ethernet cable coming in. There's a bit of heat shrink. The orange and green pairs split through the blue heat shrink, and the blue and brown split through the black heat shrink to the underside of the board and then round up to the header. This is a close-up of the power header, so you can see the blue pair is going into red ferrule, which is connected to the 12 to 24 volt input. The brown pair's got a blue ferrule on it, which is connected to the 0 volt input there. And then finally the Ethernet jack, the same as the main control box, orange pair to 1.2, green pair to 3.6, and then that just plugs straight into the BeagleBone. The F16V4 I don't have pictures of, looks exactly the same, but it is obviously plugging into one of the network switch headers at the top and using the VX connector as I talked about before. So the other cool thing I like about this design is I can extract power from the line anywhere I need and pass it on anywhere else. So my control box lives in a shed when looking at the front of the house on the left-hand side. On the right-hand side of the house, I've got a Tune2 sign. There's another two controllers over there. So I run one Ethernet line with power out to a little box that I've made, which has got a self-contained switch. So this is it here. And this switch does not require power because it's getting it from that passive PoE. So there's currently, I'm only using 5 of the 8 available ports. There is 1 power in port, 2 power out ports, and 2 regular 8P8C ports. So you can see here there are 3 of the cables have got the brown and blue pairs split out to them, which are all joined under that heat shrink in the middle. One of those is a male connector, which is the input. The other 2 have got females, and I'll talk about the connectors later. And then the other 2 cables, Ethernet cables out of here, just are direct 8P8C to 8P8C cables with all 4 pairs wired into the jack directly. So this is a close-up of the network ports. The first 3 ports on the left, which are ports 8, 7, and 6 respectively, have got just the 2 pairs in them, and then ports 5 and 4 you can see are the ones that go directly out to another AP8C outside of the box, which has got all 4 pairs wired into them. And finally, these last 2 cables, the copper-coloured cables there, they go into that heat shrink blob. The square thing on the right-hand side of that heat shrink blob is a buck converter, so that's taking the 12 volt PoE, dropping it down to 5 volts for the switch. And so therefore that switch is powered by the main control box. So this is a picture of the connector that I use. So I don't use 8P8Cs on the cables that connect from the main control box out to the controllers. I use this round 10-pin connector. It's a waterproof connector, so the female has got a sealing ring that sits up against it. You can see at the top there, there's a little metal notch for keying. And that's just so I don't mix up the regular Ethernet with my special forced PoE Ethernet. That's why I don't use a normal 8P8C. Technically, and this comes back to what I was saying before, technically I am following the Mode B or mid-span PoE wiring standard as far as polarity goes and how a lot of your power injectors do put on power. But because I'm using 12 volts, not 24 or 48, that's one difference. And secondly, I don't want to damage anything that's not expecting it. So I haven't tried putting 12 volts on the spare pins up the end of a BeagleBone, but I don't particularly want to find out how that behaves. Why did I choose a 10-pin rather than an 8-pin connector, even though I'm only using 8-pin with the Cat5? It's easier to solder. That's the number one reason. If you have a look at that picture, you can see there are 8 pins around the outside and 2 in the center. So I've got pair 1, 2, 3, 4 around the jack on those 2 vertical and 2 horizontal pairs, and nothing's connected to the middle 2 pins. If I had an 8-pin connector, I would have at least 6, if not 7 pins around the circumference and 1 or 2 pins in the center, which would just get really fiddly to solder up. So It was just solder apathy, which is why I chose that connector. 12 volts. Why did I choose 12 volts over 24 or 48, which would then make it more compatible with other PoE solutions if I've already got the polarity compatible? One, whilst most controllers or a lot of controllers will allow 24 volts on their power in, they certainly don't allow 48 volts in. And things like the Falcon, they only allow up to 13 volts on their input. They're rated 7 to 13 volts. So that's a technically limiting factor. If I was to put 24 or 48 volts into a controller that wasn't supporting it, I'll let the magic smoke out. And I didn't want to go add extra buck converters and things like that to support it to each of the control boxes. I wanted to use the native power handling techniques that they've already got in them. Secondly, as I showed before, the computer power supply in the central box is powering the controllers, but it's also powering my main show player with its 5-volt output. There was a switch on that which controls the fan inside the box, so I can turn it off when don't have a hot day. That's coming off the 12-volt output. The network switch is coming off 12 volts. The 5 volts is also driving a temperature gauge that's in the box. So it's powering everything in that control box other than pixels. So it already had 12 volts there. Let's just use it. And in the case of my middle switch that I showed, that buck converter that's using the voltage is fine running 12 volts down to 5 volts. If I was to try and run 24 volts or 48 volts, I don't even think it supports 48, but 24 volts, it would need heat sinking. That means dissipating. And I would imagine the same is with some of the controllers that support 24 volts if I was to put 24 volts into them. So that then flows on the question, well, everything's 5-volt powered. Controllers, the switch, everything like that, why not use 5-volt across the board? And the reason for that is because the 5-volt typically needs to be 5 volts. The Ethernet cables is generally 24 gauge AWG, proper 24 gauge, which is equivalent to sort of pixel stuff anyway, a little bit smaller. The voltage drop over the distances, I'm talking 20, 30 meter runs of Ethernet, that becomes a problem. When it's driving certain chips on the controllers, the buffer chips and whatever, the CPUs, they're often stepped down to 3.3 or 1.8 anyway, but they all expect 5 volts on the nose. They won't work at 4.5. They won't work at 4.2 volts. With a 12-volt input, when you go into the 12, the reason why they say it's a range 7 to 13 or 12 to 24 is there's an onboard buck converter that's dropping it down to 5. So it doesn't matter what voltage you put in the 7 to 13 volt range, it's going to put out the 5 volts that the controller requires. So if I get 11 volts or 10.5 due to voltage drop at the end of my Ethernet cable, the controller itself is still going to power up and still work. So therefore, any fluctuations or loading issues or cable resistance issues are no longer a problem. So that's why I use the 12 volts over 5. So that's basically it. It's a relatively straightforward arrangement. Use the spare pairs, bring the power down those, split it out at each end, one in, one out, and power the controllers that way. I hope you enjoyed the video. I hope you get something out of it. If there are any questions, obviously drop them in the comments below on the YouTube video. Drop me a thread on ACL. I'm Skymaster there, or catch me in the chat. More than happy to go through anything that's not clear. Otherwise, thanks for watching and have a good day. See you later.